Okay, so yesterday we learned about how the GVF convex SewerCAD solver handles simulations over time, right? Using that, those multiple steps, how it's kind of a sequence of steady states. And the unsteady flow is handled a little bit different in the explicit and implicit solvers that are found in SewerGEMS. So here is a typical situation that we have. We've looked at hydrographs quite a bit by now. So if you go to the first manhole in a pipe run, the most upstream manhole, and you pour, let's say, a bucket of water, it would look something like this, right? So flow increases and then decreases. And then let's say you run really fast downstream, just kind of following the water, and you measure there again what the flow is. You're going to see something like this, right? So this is typical of how that hydrograph would transform as it moves downstream, either a short distance or down a steep slope. But if you go really, really farther downstream, then that hydrograph is going to look something like that. It's typical of what would happen over a long distance or a very mild slope. So it just kind of moves slower. And it shifts. So the volume under that curve is the same. But how it spreads over time has changed, right? And this is what we were calling attenuation changes. So depending on the size and configuration of your system, the hydrograph shape can change quite a bit. So how do we do the flow routing? There are basically two categories. The hydrologic methods are simple, approximate methods that solve in the downstream direction. And they work for many cases. That is the case of SewerCAD that we were looking at yesterday. SewerCAD, as we learned yesterday, uses convex routing to do that. But there are some cases, especially cases that involve flow backups, where full hydraulic routing is necessary. And that's why we have the implicit and the explicit solvers that use those dynamic solvers that solve the full Saint-Venant equations. So those models are based on sound fundamentals, conservation of mass, conservation of energy, and they use the Manning's equation to calculate head losses. So what do we talk about when we talk about a fully dynamic model? We mean a model that solves the full Saint-Venant equations, which look like this. So, doesn't look like it'd be a lot of fun to solve this by hand, right? So we rely on computers for that. So let me show you some examples. When we have flow at normal depth, the steady state equations are acceptable and the conditions are perfect based on Manning's equation. So in this case, you don't really need a dynamic model unless the changes were happening very, very fast. So using a solution like SewerCAD is great. It saves you a lot of time doing manual calculations. But if you wanted to solve this network by hand, and you had the time, you could do it by hand. So unfortunately, our systems don't always behave like this. I don't think anybody has seen a system with like perfect constant slope throughout and flowing at normal depth. That's why we need more realistic models. So in situations when you have surcharged flow, it is necessary to solve more complex equations because now you don't have normal depths anymore. One of the things that could be challenging if you were to do this by hand is that the flow transitions between free surface flow and pressurized flows. So you'd have to change the equations that you're using. So that's why I think programs like SewerCAD are so useful. If you have the situation where not only you have surcharging and an overflow, then the hydrologic routing requires that the user specifies some sort of rating curve in order to model what happens at this overflow. And it's not always easy to figure out that rating curve, right? Because you need to know like what is happening in that location, what is the topography, where is the flow going to go. So it becomes a little bit more challenging. Now, in this even worse situation, the surcharge is a result of this downstream backup. So the hydrologic routing doesn't work, and in that situation, you need to solve the full dynamic wave equations, right? Because now we have flow going, in two opposite directions, as we see in the pipe here. So in this situation, which is why we've spoke so much about how the dynamic engines are better at solving backup problems. Okay, so again, remember that this applies to the SewerGEMS users. In addition to the SewerCAD solver, SewerGEMS gives you two solution engines to solve the dynamic wave equations. The first one is the default, which is the Bentley dynamic wave solver. It's the one we called an implicit solver. And the second is the SWIM solver, which is an explicit solver based on the EPA SWIM model. So if you need to submit your project using EPA SWIM, so it's compatible and they can run it and get the exact same results, then you can use that engine, but within our product. Okay, so just to reiterate, the real power in those dynamic wave solvers are the ability to handle special conditions, such as surcharging, and because those can cause problems with other problems, right? So things like dry pipes, drop structures. Dry pipes can be a problem because flow and depth go to zero. Drop structures are a problem because they represent a discontinuity in the water surface. So, just think of if you were doing this by hand, it would be actually quite challenging. Yesterday when we talked about using or recommending that you use the GVF convex solver, the SewerCAD solver, anytime you have pressure situations, we explained that it's because it uses a true pressure solver, and that the dynamic wave solvers used kind of a trick to model pressure flows. So this is how we model surcharging or full pipe flows. So we assume that a pipe kind of has this invisible pre-cement slot, is what it's called, and that way we can, the volume of water there is negligible because this would be like 1 millimeter wide, and the idea there is that we can create a continuity with the water level. All right. When you start a simulation, your pipes start with zero flow. We can modify that a little bit so that it's not a drastic change. When you become used to running these simulations, you'll be very familiar with something called discontinuity or continuity error when you run this solvers in SewerGEMS. And it's precisely because between time step and time step, it can't really converge. So to avoid that, we recommend that you use what we call transition start. So it's a way of warming up the model. And, you can try different times and really just kind of do some experimenting. Again, if you are getting those continuity errors. All right, what other things can you do in addition to that warm-up time? Avoid very short pipes. Try to make the computation time as short as you can. Let me just tell you something. If you ever run into that discontinuity error, come back and try all these things. Again, you have this in the PDF, but leave the default values because this requires a little bit of experience and practice to just kind of calibrate those well. So leave them as the way they are, and if you have problems with the continuity, come back and modify them.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.